So today we're going to take enthalpy that we talked about yesterday, talk about it specifically in the context of molar enthalpy with a focus on combustion reactions. So that is what we're doing today. So we are going to talk about the amount of something that there is. If we're talking about an enthalpy change, it depends on the amount of reactants involved. So question number 3 in the homework from yesterday really depended on the amount. So when we're talking about amount, we don't mean how many milliliters, we don't mean how many grams, we mean specifically how many moles. Hopefully you're like, oh yeah, moles, that's what you always calculate in chem all the time. And it's not news in this course that that is what we're going to do a lot of the time as well. So yesterday we saw the reaction for photosynthesis, and so I've repeated it here. In this particular reaction, I'm producing 1 mole of glucose. How do I know there's 1 mole? Well, there's no coefficient in front of glucose. That means that technically it's a coefficient of 1. So the number of moles of a substance could be determined by its coefficient in a balanced reaction. Now that's how much energy, that 2,802.5, oh, I'm so sorry. See, this is my French coming through. If there's ever a comma and you really think it should be a decimal point, it should be. I just have neglected to notice that because my brain forgets which language I'm doing. So like we saw yesterday, it's endothermic. 2,802.5 kilojoules have to be absorbed. That's for 1 mole of glucose. If I wanted to make 2 moles of glucose, I would have to take everything in that reaction and multiply it by 2, including the energy. If I did that, well then it would take 5,605 kilojoules, that 2,802.5 multiplied by 2. So the idea here is that the enthalpy change is proportional to the amount of substances that are reacting. If the amount, so the number of moles, changes, so does the enthalpy. Now you might not have needed a formula to come to this logical conclusion that we came to for photosynthesis. Well, if I want twice as much glucose, I need twice as much energy. However, there is a formula, and that's what we'll talk about on the next slide. So before I go there, does anyone have anything that they would like to ask about this idea of amount and how enthalpy depends on amount? So with a focus on balanced chemical reactions like the one that we had for photosynthesis, we could start calculating enthalpy changes. And we're going to do this first when we know the thermochemical equation. That means that I know what delta H is, and I know my balanced equation. If I don't know one of those things, we can't use this formula, not yet anyways. And the formula is at the top of the page. Delta H the enthalpy change in kilojoules, N, which represents the number of moles, measured in moles, so I'm not going to write it twice, and delta RH, which will be our molar enthalpy in kilojoules per mole. So when you're using this formula, it's important that you recognize whether you have a value that's just in kilojoules or whether you have a value that's in kilojoules per mole. And the first thing that we'll use this formula to do is to figure out the molar enthalpy of reaction. Now, because there's a little r here, we're talking just generically about reaction. But you might remember yesterday I said that little letter can change depending on the type of reaction. If I want to find my molar enthalpy, I just have to manipulate this formula. So essentially, I divide both sides by n, and it gives me this. So that's the formula that we're going to use for this first example here. This is a combustion reaction. It's not your typical combustion reaction because it doesn't have a hydrocarbon at the beginning, but it is still combustion. It's just a different kind. In this reaction, because ammonia is the thing that is combusting, instead of CO2, I have NO2. You wouldn't have to memorize this reaction. I just want you to see that it's really similar to hydrocarbon combustion. In this reaction, all of these substances have coefficients in front of them. And remember, the coefficient is going to tell us how many moles of a substance there is. So we're going to determine the molar enthalpy for each reactant and each product in this reaction. I'm going to do the first one, and then you're going to do the other three yourself. So I'm going to start with ammonia. If I want to determine the molar enthalpy of reaction for ammonia, I can't just look at that value of delta H at the end of the reaction. I wouldn't put negative 1,134.4. That's how much energy it is for 4 moles of ammonia, but I want to know for 1 mole. So I'm going to take my formula, and I'm going to replace delta H with negative 1,134.4 kilojoules. And I'm going to divide that by N, the number of moles of the substance I'm dealing with, 4 moles of ammonia. It's good habit, especially when there's multiple substances, to say which substance you've calculated the number of moles for. The reason I say this is because sometimes you might have multiple calculations going on, and it's good to know which value goes with which substance. Now, if you do this calculation, you end up with negative 283.6 kilojoules per mole of ammonia. And that would be my final answer for ammonia. How about molar enthalpy here? Okay, I'll tell you this. There's always a question like this somewhere on my tests, my unit tests, and on the diploma. And usually people get to a question like this and they think that it's harder than it is because they forget that you can figure out molar enthalpy simply by taking delta H and dividing by the coefficient. So even though it's a pretty basic idea, it's one that will come back for sure. So we're going to keep using the same reaction, so you probably don't need to rewrite it. I did just so we could look at it again. And we're going to start calculating some other things based on that reaction. So now that we know the molar enthalpy of reaction for all of those substances, we can use those values to calculate other things. So in the first example, we're looking for the enthalpy change. Notice it didn't say molar enthalpy, it said enthalpy, and that's a big important distinction. That means I'm looking for an answer in kilojoules. not in kilojoules per mole. And it's giving me a number of moles of ammonia. Now, I calculated the molar enthalpy based on the balanced reaction, but now I have a different number of moles. Does that change what the molar enthalpy is? It doesn't. The molar enthalpy is the molar enthalpy. I can change the number of moles. That will just change how much I have overall. So I can reuse the value of the molar enthalpy of reaction that I calculated before. So those numbers that you calculated, we're going to use them over again. So I know the molar enthalpy for ammonia. I'm looking for the enthalpy change, and I know the number of moles. That means I can use the formula the way it was written and simply fill in 2.18 moles of ammonia times negative 283.6 kilojoules per mole of ammonia. You'll notice, like I did before, I'm writing the moles of what so that I'm sure that I'm using the correct substance. In particular, because I had 4 different substances here, I want to make sure I'm using the right value. That way, when I cancel out my units, moles of NH3 and moles of NH3 cancel out, and kilojoules is all I have left, which is what I want. So in this first calculation, I should end up with negative 618 kilojoules. This time, because I had a measured value, that 2.18 moles, it's not coming from the balanced reaction. That actually has 3 significant digits in it. That's why I gave 3 digits in my answer. Now that one is pretty straightforward because you only had to do one step of calculation. The second one asks you to do a bit more. Still using the same reaction that we were using before, we're looking for the enthalpy change. So not molar enthalpy, but enthalpy change. That means we're looking for delta H in kilojoules. So I say to myself, you probably want to use this formula. Cool. Do I know all of that information? Well, I know the molar enthalpy of reaction because we figured it out previously. This time we're looking at nitrogen dioxide, so the NO2. And for the NO2, the molar enthalpy was the same value as it was for ammonia. And that's because it had the same coefficient. So I say, great, I should be able to use this formula. Oh no, I don't know how many moles there are. I know what mass I have of nitrogen dioxide, but that's not the same. Does anyone remember how I can convert a mass into a number of moles? Maybe? It is. So I'm going to go on the side here and do a little calculation so I can figure out N, because I didn't know what it was, but I have enough information to figure it out. When you have a mass of something, you can't assume that you're following the balanced reaction. Because someone might say, well, yeah, I just look at how many moles there are in the reaction. But because we have a mass, we know that we have a different amount than what the balanced reaction says. So I start filling in this formula. Okay, cool. 25.0 grams divided by, oh man, what is the molar mass of nitrogen dioxide? You probably want your data booklet so that you could look up on the periodic table, which is inside the front cover, the molar mass of 1 nitrogen and 2 oxygens. So if I want to know the molar mass of nitrogen dioxide, right, 1 nitrogen, 2 oxygens, I would look up nitrogen's molar mass, which I don't know if you noticed, I knew without looking at my data booklet. You're not impressed. is 14.01. And the molar mass of oxygen, which is 16.00. And both of those have grams per mole as their unit. I would recommend, when you're doing a molar mass, to do it as its own calculation. If you notice, the way I wrote it in here, there's lots of adding and multiplying and brackets that you would need. It just invites mistakes to happen, even if you know what you're doing. So I would recommend doing it on the side by itself before you do other calculations. So if you want to know the molar mass, this number is actually 46.01 grams per mole. Now here's another topic. If you've said to yourself, hey, I know I'm supposed to know this, but I just don't feel comfortable figuring out molar masses, and you want to practice, please tell me. I'll give you some worksheets to practice. Now that we know this, I can go back and figure out the number of moles that I have. The number of moles is 0.54 blah blah, so many decimal places. Notice what I did. I did not write down all of the decimal places that my calculator gave me. I wrote some dots to indicate that I know that that answer had a whole bunch of decimal places. Do not round your answer here. Store this number in your calculator and then use it in the next part of the calculation. If you don't know how to reuse an answer in your calculator, please tell me and I will try to help you on your calculator. If you have a TI, you should have a button on your calculator. It's usually a second function button that says ANS. That means take the answer that I just got and use it again in a calculation. That's what you should do. If you round your answer in the middle of a calculation, you might get an answer that is 0.1 off of the correct answer, and if it's a numeric response, you'll get it wrong. And I don't want that to happen to you, so don't round. Now that I know this number of moles, I'm going to take this number of moles and pop it into the formula that I said I wanted to use at the beginning. So I'm going to take my 0.54 unrounded moles of NO2 and multiply it by the molar enthalpy. And then I'm going to finally calculate my answer. When you multiply those two numbers together, you should get negative 154 kilojoules, which is my rounded answer. I used 3 digits because my measured value of 25.0 grams also had 3 digits. Now this example, same reaction. We're going to talk about ammonia, so we already know the molar enthalpy of ammonia. We are looking for what mass of ammonia. So I say to myself, well, if I want to figure out mass, we just used this formula. I should be able to rearrange that so that I can find mass. And that's what I'm going to do. So that's my goal. I want to calculate the mass of ammonia, and that is the way that I would like to do it. So I ask myself, okay, do I know either of those numbers? Well, if I read the question, there's no moles, so I'm going to have to do something there. Molar mass, even though it's never in the question, you can always figure out if you know which substance it is. So we'll start with molar mass because it's the easier of the two. We are talking about ammonia, NH3. When you figure out the molar mass, do not use the coefficient. So even though there is a 4 in front of ammonia, that's not part of the molar mass. The molar mass for ammonia would be 14.01, which is nitrogen, plus 3 times the molar mass of hydrogen, so 14.01 plus 3 times 1.01 gives you 17.04 grams per mole. So 1 nitrogen, 3 hydrogens. I did not multiply it by 4. Now to figure out the number of moles, you might feel stumped because you might say, man, I thought this formula was how I was going to figure out moles, but obviously I can't. But you have another way. the other formula that we've been using has moles in it as well. If I rearrange that formula, I can calculate moles. So to rearrange that formula, I divided both sides by delta RH, and that essentially moved it to the other side. So if I want to know the number of moles, I'm going to take the enthalpy change in kilojoules and divide it by the molar enthalpy in kilojoules per mole. Here's the enthalpy change, my delta H, and I already calculated the molar enthalpy in the first part of this question. So, negative 4.50 megajoules divided by negative 283.6 kilojoules per mole of NH3. Now, there is an issue here. If I had units like joules and kilojoules, one of them didn't have a prefix and one of them did. But now I have two different prefixes. That causes an issue. It's a little bit harder to combine megajoules and kilojoules. So when you have units and they have different prefixes, you should change one of them. I usually choose to change the bigger unit because I don't like decimal numbers. I like big numbers. They're easier for me to look at. So instead of megajoules, I'm going to change that unit into kilojoules. Now, how did I know that it was 10 to the power of 3 kilojoules? Well, if you consult your data booklet, or you just remember, it tells you that a kilojoule is 10 to the 3 and a megajoule is 10 to the 6. The difference between them is 10 to the power of 3. That's how I knew that that's how I was going to change my unit. Now that I have good units, all I need to do is divide those two numbers. And just like the last question, I will not round the number of moles that I get. Otherwise, I could end up with the wrong answer at the end. In this calculation, I would find out that I have 15.867. And then the decimal continues, so I make a note that I'm going to save that answer in my calculator. That's how many moles I have. Now, I have the number of moles, and I have the molar mass. Those were the two things I needed to calculate the mass. So I can go back to the formula I wrote at the beginning and put those two numbers in. So, my 15.867 moles times 17.04 grams per mole. And you should end up with an answer of 270 grams. Now those three examples show you how to calculate with that formula, but along with moles or along with mass. It would be pretty typical for you to have to calculate the number of moles, let's say, or to figure out a mass, because generally in chemistry, you don't have a machine in the lab that measures the number of moles. You have something that measures a mass. And so usually having to convert between mass and moles is something that will happen. Does anyone have questions about any of those examples we did there? Okay. So we just have a little bit to say about combustion. So like I said, there is another example, but I think I'm going to leave it for now. We could always come back to it if I think we need it. Now, all of those examples were just about molar enthalpy in general. But most of the time in this unit, we are going to be talking about the molar enthalpy specifically of combustion. And when we're doing that, the little r will change to a little c. Nothing about the calculations will change. We would just be using a different subscript as part of our original formula. Now, it's expected that if someone said molar enthalpy of combustion, you know what that means. So the definition is this. It's the enthalpy change associated with the complete combustion. You might be aware, but sometimes combustion reactions are not complete. A complete combustion reaction is the type that you have seen up until this point, where something reacts with oxygen and produces CO2 and water. That's complete combustion. The other part that really is important is that there is 1 mole of a fuel. Now the fuel can change, but the general reaction for a combustion reaction would be a fuel plus oxygen gas produces CO2 gas, water vapor, and energy. You might not have included energy before, but now we know that combustion reactions are exothermic, and the energy will be a product at the end of the reaction. Now, most of the time, combustion is done as an open system. And then the following point explains to you what an open system is. An open system is when the combustion products, specifically gases, are allowed to escape. So essentially, whatever is burning is not inside of a sealed container, but rather there is some sort of outlet through which heat and through which gas could escape, like a car engine, like a barbecue. Almost all the time, combustion will be in an open system. Sometimes we'll see the opposite of this, a closed system. And in fact, one of the questions in the assignment for today mentions it, and then we'll do a lesson on it a bit later on.